All right, here we go. Let's sketch this. Let's do this problem where we're sketching the graph of two parabolas, and then we're going to find the area between those two curves. Now, I'm not using graph paper, and the reason is that these numbers become large, and if I use the squares in the graph paper, it doesn't even fit on the page. So I'm going to sketch some graphs that aren't actually quite even aren't even to scale, because if I want to make them to scale, they're not going to really fit in. So it's a little bit, less precise this way, but it also gives me a little bit of freedom when I do it like this. So let me sort of, roughly, it's not as beautiful as if I did it with graph paper, but I roughly have this y equals x squared, and that's the easy one for me, I think everybody to sketch that. Now this next one, y equals negative x squared plus 18, is a down-facing parabola. I know it's a parabola because it's a quadratic, a second degree polynomial. I know it's down facing because the lead term, negative x squared, has a coefficient which is negative. Now, so this guy is going to, let's pick out green. Okay, this is going to look like this. Well, actually, I don't quite know that it lies above the x-axis, so actually I already did this problem. But the reason, let me find x-intercepts. So without doing calculations, how do I know it even lies above the x-axis? So let's hold off on that x-axis, but it is down facing. So let me see whether if I set this equal to 0, whether I get, what I get. If I factor out negative x, when I set it equals 0, I'll get negative x times x minus 18 equals 0. So x equals 0, x equals 18. Okay, so it does intersect the x-axis at 0 and 18. If you want, the parabola comes pretty easily because the vertex of the parabola, at least the x-coordinate h, comes easily because it's the midpoint between 0 and 18, which is 9. Do that in your head. But let's now look for the intersection. So also I need to include on this the y-axis. So certainly looking at those two graphs, even though they're not to scale, the x and y-axis aren't really to scale, but looking at these two graphs, you can see they're going to intersect. Okay, so just by looking at them, one of them is facing up parabola. The other one, the down-facing parabola. Not to scale the x and y axis. The shapes aren't that good, but the idea, I think, is good. In graph paper, I would have to have small squares if I'm going to use graph paper. Okay, I was just thinking about putting that all together. Now, if you carefully sketch the graph, you can actually see, maybe even guess what the point of intersection is. But I didn't sketch it that carefully, and so let me find the points of intersection by setting these two functions equal to each other, and it's a pretty easy calculation, but it's good to know anyway that the way you find the points of intersection is by setting the two functions equal to each other and solving for x. So let me be careful about all of this, that I'm doing everything properly with the plus and the minus. It makes a big difference. Okay, so if I factor out 2x, I get 2x times x minus 9 equals 0. So x equals 0 and x equals 9. And so, in fact, they intercept right at this, at the vertex of our downward-facing parabola. Now, do you want to find the y-coordinate? Might be fun, but don't really need to. In fact, but it's easy actually, because if you put in x is 9 for y equals x squared, you get 9 squared is 81. But there's no reason to do that with our problem with integrating, which is what we're trying to do is we're going to find the area by integrating. And the reason I find the points of intersection is because I need to know those bounds. This guy here is the y equals negative x squared. Well, how am I going to fit that in there? Just zoom in and write smaller. It's a good idea. So I'm just going to try to label this nicely. It's a little bit frustrating to spend so much time on doing a graph, and then I think the question is reasonable to say, well, how good does my graph have to be? I mean, I got the general idea, downward facing parabola, upward facing parabola, didn't get the x and y axis scale. I mean, to keep in mind that, okay, the one in purple is y equals x squared. At 9 squared is 81. So so that point of intersection is 981. There's no reason at all to write down the y coordinate of that for us to solve the problem. But anyway, what I'm getting at it is it's not to scale. But okay. Now sometimes some books ask you to draw a little rectangle, so I can do that. Oh, maybe I can't. But anyway, you draw a little rectangle there. The width of that rectangle, the dimensions of our rectangle are going to be, you could say it's delta x. I'm going to just sort of skip ahead and say it's dx for a rectangle. And then the top function is negative x squared plus 18x. And the bottom function is x squared. So you subtract to get that height is the top minus the bottom. The problem is my writing is not a little bit messy. But that's the height of that. Okay, so you take the top function, which I have in green, and you subtract the bottom function, which I have in purple, and that gives you the height of a rectangle there. And so then how do we find the area? Well, the area is we integrate from a to b, and we take the top, which I'll call f of x, and the bottom, g of x, and you integrate that from a to b. Well, it was important for us to find out what a and b are. A and b are 0 and 9. And then the top function is negative x squared plus 18x minus x squared. Okay, so we had to find those points of intersection. I think that there's a good argument to make that I overdid it by finding, when I did the downward facing parabola, by finding the X-intercepts, but it was sort of easy. But I had to find the points of intersection. It's a downward facing parabola, and but you don't have to get the best picture. Okay, now this should be a pretty easy integral, except the numbers are sort of big. And, maybe there's fractions, and that's unfortunately maybe the part where I'll be likely to make a mistake, which I don't like at all. But I use the power rule to integrate. And so then I'm going to write negative 2/3 x to the third power 0 to 9. I'm basically using the distributive property by evaluating just each piece, each term. X to the third, I'll go from 0 to 9. 18 divided by 2 is 9, and then I'll do x squared from 0 to 9. So looks like I'm going to get some big numbers, but maybe I can try to be clever about this. So I have 9 to the third minus 0 to the third when I put in 0 and 9, plus 9 squared minus 0 squared. So I'll get negative 2/3, 9 to the third, plus 9 times 9 squared makes 9 to the third. What if I factor out 9 to the third? It seems like that might make everything I do a little easier. That's going to make 9 to the third times negative 2/3 plus 1, so it's 9 to the third plus 1/3. Or some people are like, hey, just use a calculator. What's the big deal? So this is 9 times 9 times 9 divided by 3. So that's 81 times 3, which is 243. I don't have the answer in the back of the book right in front of me to look at. This is a problem. This is an odd problem from Openstax Calculus, Volume 1. So I feel like I did that right, but I don't know. We'll see if I look that up in the back of the book, and I didn't, then I guess I'll redo the video. But let's just say that's correct. And we found the area between the two curves. We sketched the graph. So I didn't label this one. Well, I sort of did above. Right here, I'm gonna just move that down. Okay, so I think that does it. Here we have y is a function of x, and y, you have two functions, both functions of x. We sketch the graph, we find the region. The goal is to find the area of that region. I sketched it, but I want to find the area. I subtract the top function minus the bottom function, and I have to find the bounds of integration by integrating, by finding the points of intersection. So I integrate between those bounds of intersection, between those intersection points. All right, that's all.